In the previous video, we started our discussion of the different PV technologies. We discussed the abundance of the elements used for crystalline silicon and the record efficiencies. Now let's continue with the thin film technologies. Thin film solar cells are made from films that are much thinner than the wafers that form the base for first generation PV and therefore use much less material. The processing techniques used for thin film solar cells are very different from the techniques used for crystalline silicon. Please note that all the concepts and technologies we introduce here will be discussed extensively later in the course. We'll start with thin film silicon. Rather than the crystalline silicon structure of the first generation PV technology, thin film silicon has an amorphous structure. These amorphous silicon solar cells use many of the same materials as are used in crystalline silicon. Additionally, hydrogen is used for the passivation of the amorphous structure, and zinc is used for the transparent conductive oxide layer or TCO layer. Another class of thin film solar cells are the chalcogenide solar cells. The term chalcogenide refers to all chemical compounds consisting of at least one chalcogen anion from group 6 and at least one or more electropositive elements. The chalcogenides are a very large group, but in this course we will focus on the two most important technologies. First is the cadmium telluride, which currently is the thin film technology with the lowest demonstrated cost per watt peak. This class of chalcogenides uses materials from group 2 and group 6, and also elements like aluminium, zinc, and oxygen for the TCO layer. The second group of chalcogenide solar cells are the chalcopyrite solar cells, which consists of elements from group 1, 3, and 6. Foremost among these are the copper indium gallium diselenide solar cells, or CIGS for short. So how about the elemental abundance of these technologies? Thin film silicon makes use of the same elements as crystalline silicon with the addition of zinc, which is a major industrial metal, and hydrogen, the most abundant element in the universe. As we can see, thin film silicon uses no rare or toxic elements. Next is cadmium telluride. While the supporting materials like sulfur, aluminium and zinc are abundant, cadmium and telluride are not. Telluride is even among the rarest stable solid elements, with an abundance of about 1 atom per billion silicon atoms. This is comparable to the abundance of platinum. Furthermore, elementary cadmium is toxic, and it is very important to prevent cadmium from entering the ecosystem. CIGS faces similar issues. Copper and gallium are major industrial metals, but indium, selenide and cadmium are much less abundant. In addition, the current thin film display industry depends on indium as well. Because of the scarcity and toxicity of required elements, the upscaling of the chalcogenide PV technologies might be limited. The efficiency of these thin film technologies has increased steadily over the last couple of decades. The performance of CIGS and CadTel solar cells is very similar, with a record efficiency of 23.4% for the CIGS solar cell from Solar Frontier and 22.1% for the cadmium telluride solar cell from First Solar. The performance of thin film silicon solar cells is lower, with a stabilized record efficiency of 14% achieved by ICE. The addition of the term stabilized will be explained later in the course. Next we discuss the 3-5 technologies. As you will learn later in this course, this type of PV technology is mainly used in multi-junction configuration, in which multiple 3-5 alloys are used. The 3-5 alloys are based on group 3 elements with 3 valence electrons, like aluminium, gallium or indium, and group 5 elements with 5 valence electrons, like phosphorus and arsenic. As some 3-5 concepts use a crystalline germanium wafer as a substrate, it might not be considered as a real thin film PV technology. However, the 3-5 base absorber layers can be considered as thin compared to the thickness of a crystalline silicon wafer. If we look at the elemental abundance of 3-5 technologies, we see that only aluminium and phosphor are really abundant. Gallium, arsenic and germanium are not rare or precious, but they are much less abundant than silicon. Indium, as we discussed earlier, is rare and in high demand. Gallium arsenide is therefore a very expensive material. Moreover, arsenic is highly toxic and it is strongly suggested that gallium arsenide is carcinogenic for humans. So why do researchers still pursue these III-V technologies? Let's take a look at the record efficiencies. Of all the thin film technologies, the III-V technology results in the highest conversion efficiencies under both AM1.5 standard test conditions and concentrated sun conditions. The current record solar cell by NREL has a conversion efficiency of 47.1%. Consequently, the expensive III-V PV technology is mainly used in applications where the generated power density is the most important metric, such as for space applications and concentrated photovoltaics. Finally, we will consider organic and perovskite PV technologies. For organic PV, the used absorber materials are either conductive organic polymers or carbon-based organic molecules. Perovskites are an organic inorganic PV technology that has received a lot of attention in the last decade. A wide variety of materials are used for organic PV from different groups. Generally speaking, even though organic solar cells themselves use cheap abundant materials like carbon, they require very expensive encapsulation materials and contacts to protect the organic materials from humidity, moisture and air. Some of these materials like platinum, ruthenium and iodine are very rare. This constraint limits the industrial application of organic PV. Let's look at the record cell efficiencies again. We can see that, apart from dye-sensitized solar cells, the organic PV research has only been going on for the last decade and a half. In that time, organic solar cells have reached a record efficiency of 11.5% by Hong Kong UST, and UNIST has reached a record efficiency of 25.7% for a single junction perovskite solar cell. It should be noted that this is an initial conversion efficiency and not a stabilized efficiency, since no stable efficiencies for a period exceeding a few months have been reported for perovskites to date. That concludes this introduction into the different PV technologies. During this course, you will gain an in-depth understanding of the various module architectures, manufacturing and processing method, and advantages and limitations of each of these technologies. So I hope to see you again in the next video.